Hello, it's David. So at the tail end of my last video, I was demonstrating the board that I built here, the PiStorm STE, a couple of bodge wires on the bottom from this one now. It's been through the wars a little bit, but could get it to boot up and get it to do the basics, but what I couldn't get it to do is be stable. So I thought, is there a problem here with my board? I've reflowed everything, I've gone over with the magnifying glass, the CPLD pins, all the normal sort of things. This bodge wire was because I actually hot wired in an external 5-volt supply in case it was that, and then tried to put it back and messed things up. So this is I can't find any fault with this. This one to me seems fine. So what I've done is I've reverted my STE to the original development state, which is the a PLCC to DIP64 adapter here. This is the Exos version because it happens to have the pull-ups on it. Actually no, my motherboard does have the pull-ups on it. I could have used that one. I've also got my own design for one of these, but anyway, this is the Exos one. We've got a traditional PiStorm in here with just an extra standoff, and I've got a Pi 02 here. Just that's what I'm using at the moment for testing. I'm not trying to get speed, I'm just trying to get stability. This is, I know it's black, but this is actually just a 5-volt booster rail over there to make sure that we're not going to be throttling at all. And I want to see whether this is stable. And unfortunately, well, the answer is no. So there we go. We'll hit reset. Amitos 1.2.1. Don't worry about that freeze, that's because there's no keyboard in, and there we go. Straight away, panic, bus error, bus error, bus error. So I've tried different adapter boards, we've tried different PiStorm boards, tried different Raspberry Pis. Obviously my board is a combination adapter and PiStorm, and that's the one I'm struggling with. So I think what we'll have to do is just try this in a different machine. So I think it's probably time to turn to the STFM. So in an attempt to test the old PiStorm on a different machine, I'm going to try and get the STFM motherboard that I have here up and running. Ever since I installed the ROM switcher here and socketed the CPU, there's been a bit of an intermittent problem where I'll put it in one position and it'll boot, put it in another position it won't. Now that sounds to me like a poor contact or a dodgy trace or a dry solder joint or something. So I just took it inside to work on it and it didn't boot. So I'm going to set it up here on the desk. I've got the monitor on the background here, we've got an oscilloscope on the side. I'm going to do a bit of probing around and we'll see if we can figure out what's going on. Okay, so we've got a slightly convoluted setup here. We've got our long distance power supply feeding 5 volts in, there's a 12 volt boost there, so that should get us up and running. VGA monitor, so we've got mono output. I'm going to concentrate probably on the ROM, which is over here, and the CPU, which is here, and we've got the oscilloscope on the background here. I've taken the GoTick out because, to be honest, we don't need it to see if we get a boot screen. The board is very, actually heavily warped, I can see that, so that probably doesn't help things. So I'm going to throw the switch and see whether we get a signal. So power's on and would you believe it? It's the demonstration effect. Okay, so I think I'm going to have a bit of a jiggle around here and see if I can get it to crash. That's going to be awkward to get on the camera. So I should probably need something on the screen so I can actually see when it does die. Okay, so we don't have any keyboard attached, so I can't move anything around on the screen, but what I'm going to do is just keep watching the screen here and start tapping around locations. So I'm going to start in the ROM area, because that's one of the areas I've soldered. Just tap, tap, tap. Can't see any obvious things there, so I'm going to move across to the CPU and I'm going to start tapping at the left end of the CPU. Oh, and I saw a glitch on the screen there. Okay, middle of the CPU. Oh, hello, there we go. Okay. That's the middle. Yep, glitching. Right hand end of the CPU. Okay, not so much. Middle of the CPU does appear to be There we go, look at that. Well, I'm going to tap it and press reset. Okay, there we go, and we've fermented a crash. Emitos, blah blah blah, and then just a P. Going to just press reset again. There we go. Alright, so there's definitely something amiss, and it does look like it's CPU, which is to be expected, because to be honest, I damaged the pads quite heavily when I was trying to get that CPU off the first time around. So actually, before we turn to the oscilloscope, I think what I might do is just get out the multimeter and do a bit of continuity testing. Okay, so I'm just monitoring some of these pins on here, and this is, so it's crashed at the moment. We're in a crashed state. I'm pressing reset, and this is A4. Now that, oh, there we go. I was going to say, that doesn't look too healthy, and then it sort of like sprung to life a bit. Press reset again. Yep, okay, look, you can see there's data happening there. Then this is the next pin to it, A3. Pressing reset. Pressing reset. Oh, and there we go. So that doesn't look too positive either. This is A2. Pressing reset. A2 really doesn't look healthy at all. And then this is A1, this is the lowest address pin. There we go, look, press reset, bang, straight to life. And I see things scrolling up the screen at the moment. That is now, that's A2. Okay, that looks a bit better. That's A3. And that's A4. Things are scrolling up the screen, and that's what A4 is showing us. Press reset, nothing. This, I don't understand. It's actually booting up at the moment. That's A4, and it's crashed, well, half crashed. Oh, whoa! Look at that. I'm not sure I know what's going on there, unless I've got a bad contact with my probe. That's possible. I've got a bad contact with my probe. Let's try that again. That's A4. I've been probing the top of the pins, and it's crashed. Maybe actually I need to probe the socket. Just going on the pins again now. That one looks nice. That is FC0, okay. That's better. That's the interrupt, or the first interrupt. Second interrupt. Actually, that must be, yeah, no, yeah, that's one of the interrupt lines, I think. Yep. That's the E line. That's VMA. That's reset. Noisy, but should be fine. That's halt. Okay, so I actually took this away and buzzed out every single point to somewhere else on the board, primarily over here. The blitter chip, actually, obviously non-populated, this actually has most of the pins from the 68000, and otherwise I traced them off to various other places like the glue, where the rest of the pins go, and I couldn't find any problems. Tapping while measuring didn't yield anything, so it's possible there's actually a short circuit between two lines, which that technique would not really show up. And I was starting to think I'm going to have to do it in pairs and tap, tap, tap. Wasn't getting anywhere. So I remembered we have the PiStorm. Now, what is the PiStorm if it's not basically software-controlled pins? So what I'm going to do is fire up the PiStorm. Here it is in situ. This is what I'm tarting up this board for. So here it is in situ. We're going to fire this up, and we're going to run some memory tests on this, and we're going to see what happens as we poke around. So we don't really need the screen for this, but what we do want to do is to be able to see the SSH session into the PiStorm itself. So let me get that set up, and I'll show you what I'm talking about. Okay, so we've got the PiStorm connected here. It's running. I can't get everything in shot because this is so reflective, so I'll just bring it in when I need it. But this is performing a memory test on the system, just a looped memory test. And you can see if I bring it in here, all these big filled green areas are errors. There are thousands upon thousands of errors. And so all I'm really going to do is just start pushing around on the board here and flexing a bit, and see if I can get, there we go, the errors to disappear. Perfect. Look at that. And that's just by holding that flat. Of course, that still doesn't tell us what's wrong, but it does show us that there's a little bit of flex on the board, and there we go, surely the problem vanishes. Now, the fact that if I push it down like that, and by the way, let it go, and yeah, loads of errors pop up again. So my thinking is that by pushing it down, what I'm probably doing is I'm flattening out the bottom, obviously, but I am pushing the top layer closer together. So the issue is probably on the soldering of the top layer, which means I really don't want to have to remove the socket, because that was a pain when I did that initially. But what I maybe can do is jumper a pin if I can figure out which one it is. So the next trick is going to be to modify the test program a little bit to print a repeatable pattern, or rather request a repeatable pattern, and we will see if we can diagnose what's going wrong on the pins. You'll see, by the way, that I've removed the ROM over here just to avoid any potential issue with that. If you know, it was an issue, because that's also my work. If I caused any problems with the board that I put in there, but you saw that was doing that with just the PiStorm and no ROM. So let's get on with the diagnostics. Okay, so we've got this repeatedly querying a single byte at address 0. My network connection is a bit patchy, so it's not running smoothly, so I've got a counter there to make sure I can see that it's actually happening. So we're getting FF at the moment, which is what's to be expected, because 0 is actually the first byte of the ROM. And if I manipulate the board off camera here, it's still pretty solid at FF. So that's interesting. That says to me that your data lines, actually no, I suppose it could still be, you know, basically all the address lines are one thing and all the data lines are one thing, and so we end up with a consistent pattern. So if there is some crosstalk, then you'd expect that sort of behavior. On the other hand, if one of the address lines is tied to ground or is touching ground, and you get 0, then that would work. And if one of the data lines is touching 5 volts, then you'd get FF, so that would work. So it's narrowing down a little bit what we're looking for, but it is not particularly interesting. Let's try looking at a different address. Okay, so now we're looking at hex 1000, hex 1000, and you can see here we go. So we're getting mostly 77. We're going to manipulate the board. Still 77. Bit of a pause, bit of a break. While we wait for the network. There we go. Yep, 77. So that again is quite a good sign. So 1000, we appear to be getting solid results. Let's try another address. In fact, actually, let's poke a value into memory there and see what we get. Okay, I've just poked AA into that address, and there we go. Yep, we've got AA back, and it's manipulation of the board, not seeing any changes. So the obvious AA is every other byte in one order, every other byte in the other order is 5-5. So let's repeat that process, but with 5-5. And there we are, we're getting 5-5 back from that byte, and I am once again manipulating the board, and I'm not seeing any problems. So, good. What we've basically shown there is that the lower half of the data lines are probably okay. We could try peaking 1 byte higher and test the higher lines. Okay, so I've poked the value 5-5 into address 1001, and we're getting that result back. I've poked 00 into address 1000 so that we can prove that it is genuinely, there we go, 00, that it is genuinely writing. So there's 5-5, a bit of board manipulation again, and I'm not seeing any changes. So to me, again, this implies we're looking at address lines now. Okay, let me just test AA. That's yeah, only fair. 1001, and we'll go AA so that we've got the complement, and we can run the peak on that again. There we go. We're getting AA board manipulation. Yep, AA is all the way. Excellent. Okay, so I've captured the output of a Atari test there, and this is on the right test, and sorry for the escape characters, but slowed it down so I could look at specifically the byte tests. There's actually another pattern we can see here. C should be 8. C should be 8. C should be 8. C should be 8. Huh? And 6 should be 2. 6 should be 2. 6 should be 2. So we can actually have a look at what that means on paper and see if we can actually figure out what's going on. It could be data lines, but it's more likely, I think, to be address lines. And so where this is asking for F8, it's actually asking for, where it thinks it's asking for F8, it's actually asking for FC. Well, what this is doing, you see, is it's trying to write the last two characters, the last byte, if you like, of the address into that address. So into this one ending 78, it's trying to write 78, but it's retrieving 7C. And the same down here, F2, it's trying to write F2, but it's getting F6. F8, it's getting FC. So it's writing what it thinks is 78278, but then when it reads it back, it's getting 7C. Now, if we look at actually how let's look at FC in this case. If we look at how FC and F8 are written out in binary, we can see that there's this 1-bit difference. We've got 1, 1, 1, 1, that's F, that's the same on both. We've got 0, 0 down here because they're nice even numbers and actually they're multiples of 4. But here, the 4-bit is different. So this would be address line 0, 1, 2, A2. This is different. That's the only difference between FC and F8, that one line being high for FC and low for F8. So as it goes up through the sequence of addresses, it'll get to F8 first, and it will write F8 into what it thinks is F8, carry on for a few steps, and then it will get to FC, and it will try and write FC into what it thinks is FC. However, if this A2 line is always stuck high, for example, then what it thinks it's writing into F8 will really get written into FC. And when it thinks it's reading from F8, it will really be written FC, be writing into FC. So F8 could very well be being written into the FC area address, but then when it gets to writing FC into that address, it will overwrite it. When it comes back to read, both of them will now appear to say FC. So that's very similar to what we're seeing here, which would imply a problem with the A2 line, 0, 1, 2. Now, of course, this is an 8-bit test, and this is a 16-bit machine. So it's possible, of course, that the same thing could be going on the higher bits, and we're not seeing it. These are all even numbers being tested here. So actually, an even number in a big endian system like this is actually the higher bits. So this would be A8, 9. This would be A10, the A10 line. So we could start probing around the A10 line and see whether we're seeing anything occurring there at all. Okay, so well, that's the A2 line. I've done a bit of reflow on the bottom here, just doing a little bit of tidy up. Couldn't see anything particularly bad there, but I destroyed some pads when I did this the first time. My desoldering, even with the technique I used, which I'll link in up there somewhere, huge finger, was to cut off all the legs of the chip and then desolder them one at a time. But even then, I am so bad at desoldering through whole components. So yes, I have lost some pads, and I suspect what's happened is that I was getting intermittent contact there. I still couldn't find anything on the scope or the multimeter, but that's the advantage that we have of having a programmable, software-defined hardware. Basically, I could track it down to most likely being, and I've reflowed them all, so I can't guarantee it, but that pin did not have a lot of metal to solder onto, so it kind of soldered onto the through hole plating. So that's what I've done, and I'm quietly confident. Let's flip it over and turn it on. Okay, so here we go. We've got the 68,000 back in so that we can, so we're not introducing any problems of ourselves. You can still see that flex is there in the motherboard. We've got the ROM back in so that we can boot up. We've got my shonky 12.5 extended power supply here. Nothing else connected. Let's point you up at the screen and hope for the best. We should see the light go green. Yes, there we go. We've got a signal. MUTOS 20220520. That's better. Right, let's just flex the board a bit and see. Oh no, oh dear, no. I've still got a crash. Okay, let's reset. I might not have done enough. Get to the splash screen. I'm going to flex the board again. Oh yeah. No, we're still not there. I'd like to thank this video's sponsor and the supplier of my project PCBs, PCBWay. PCBWay aren't just about PCBs either, although they are extremely good at that. They also offer component assembly, CNC machining, 3D printing, and a variety of other manufacturing services. They have a number of community-focused offerings too. The Shared Project Hub is an open platform for makers to share and exchange their ideas, and the PCBWay store is a great place to pick up assembled modules. I mean, who wouldn't want a musical Tesla coil? So many thanks again to PCBWay, and I recommend you have a look at some of the links included down below. Okay, so here's the thing. I think I'd become a little bit fixated on the CPU socket here on the basis that that's what I'd added, and that's where I'd got involved and messed things up, and perhaps a certain amount of concentration on the ROMs, because again that's something that I've done. But one of the things that's blatantly obvious on this board, and I should have spotted it sooner, is that both the MMU and the shifter oh, that's not the shifter, is it? Sorry, what's that one? That's the glue, is it? I think that's the MMU, that's the glue, I believe. Might be the other way around. But from factory, they would have a metal clip over the top to hold them tightly into place. And I was just doing a tap test around the board. You know, okay, flexing here could cause it, but what about any sort of individual, more localized tapping? So I went through all the chips, all the RAM chips and stuff. And the one that really sort of tended to trigger things more often was the MMU over here. So I think that's the MMU, pretty sure that's the MMU, just because it's next to the memory. Now, okay, that's also right next to the CPU, and this area here, these address lines at the top, this is where I was concentrating. But of course, these two are really close to each other, and it could very well be that this was the problem. So I took that out with a PLCC extractor, gave it a clean up, gave it the treatment with the old wire brush here, sprayed some contact cleaner in, reseated, and this has now been running happily for about an hour. No trouble at all there, and flexing the board here, I'm just flexing it off camera. Hold on, let me lock the camera, I'll do it with two hands. We go, flexing the board, and stable. So I think I may have been barking up entirely the wrong tree, and I'm quite glad I didn't indulge in a load of mods on the board. I was thinking about soldering wires on the back of the CPU socket, put them to the ROMs, maybe taking other ones out to the sort of unpopulated blitter over here just to, you know, rule out a break part way through. I think all along it's just been a slightly dodgy PLCC MMU, and a little bit of contact cleaner and tidying up has done the trick. Fantastic.